Welcome viewers. Today we shall be discussing on the module number 34 on the topic multicollinearity. In the framework of a multiple regression model, we have observed that all the variables are affecting the dependent variable along with an error term. So since we are considering more than one independent variable, which is a point of departure from bivariate regression model to multiple regression model, there is a possibility that the variables are correlated with each other. And if this problem persists, we call it a problem of multicollinearity. And in such case, we are violating basically the OLS assumptions. So to explain on the problem of the multicollinearity, we shall be visiting on the concept of this term, what are the consequences on the OLS estimators, and how can we correct this problem. So in order to proceed for this, we go for the concept of multicollinearity. Here we observe that multicollinearity is basically affecting the individual regression estimates. So it is basically the collinearity or the association among the independent variables that we consider in the study. So as a result of that, first of all, in any data analysis, we identify the regressors or the explanatory variables. After it is being identified, we proceed for the estimation. And after the estimation is being made out, we go for the appropriate variables which are correlated with each other. So this basically captures the element of correlation and how the multicollinearity actually poses a problem. And if this problem persists, then the individual effect of any independent variable cannot be figured out. And so there is a corrective procedure also meant out. So now we move on to this particular slide where we observe a kind of a Venn diagram to show the representation of how the independent variables may be related. If we refer to point number A, where we observe that no collinearity, that means we consider three variables where x2 and x3, which are basically affecting the dependent variable y. So we observe that x2 and x3 are individually affecting y, but there is no common or intersection between x2 and x3. So since there is no intersection between x2 and x3, we say that x2 and x3 are independent of each other or there is no collinearity between them. Now if we proceed for point number B, which says low collinearity. That means here also we observe y is the dependent variable where x2 and x3 are affecting y indeed, but the commonality between x2 and x3 is very less. So the intersection zone is shown by the shaded portion and which is very small. And since the shaded portion is very small, we say that there is a low collinearity between them. But actually it affects partial multicollinearity problem. If we move to point number C, which says moderate collinearity, because here the shaded portion is comparatively bigger than the point number B, where we observe x2 and x3 are related with each other and they are basically collinear. Now in point number D and point number E, we go for the high and the very high cases. In point number D, we observe that x2 and x3 are correlated with each other, and not only that, the shaded region or the intersection region is quite bigger. And in point number G, we observe that x2 and x3 are highly correlated with each other. That means in this particular slide, we are getting a pictorial representation of how the independent variables are related with each other, and we are actually proceeding from no collinearity to very high collinearity. And this actually projects the problem of multicollinearity in the data set. In order to go for this, we need to understand why this problem is important or what is the relevance of this multicollinearity problem. In order to do this, we observe two important findings. If we go for a perfect multicollinearity problem, then we will find that only one variable captures the effect of all the others, and as a result of that, we cannot find out the value of the estimates. The result is undefined or indeterminate, and the standard errors are infinite. This happens if one variable is actually taking care of all the others. For example, in a health sector, suppose we want to do our work on how the life expectancy gets affected. So if we take all the health related variables, it may observe that the government expenditure is affecting all of them, and thereby the variables are correlated with each other. So one variable takes care for everything. That is an example of a perfect multicollinearity. Secondly, multicollinearity is less than perfect. It means that suppose we have x1, x2, x3, x4 are the independent variables, out of which x2 and x3 are correlated with each other. That means x1 and x4 are independent, but x2 and x3 cannot be taken together because they have a strong association between them. So here also we observe that the standard errors will be large, but that also will project some kind of consequences or indications or detection of the problem. So here we observe that multicollinearity can be perfect or it can be less than the perfect, and accordingly the corrective steps to be taken up. So now the question comes, why multicollinearity is needed? Why is it important? Because we need to understand in a classical linear regression model the assumption of no multicollinearity. So among all the OLS assumptions, this is one of the basic assumptions that there is no multicollinearity. So the problem is why there should be no multicollinearity. If it is there, what are the problems we can expect? So if it is perfect, then we have already observed that the regression coefficients are indeterminate. That means we cannot say that the regression coefficients are determined and the standard errors are infinite. So this basically questions on the accuracy of the estimates. And secondly, if they are less than perfect, then also the standard errors will be large, but the estimates will be determined, it can be computed, but the standard errors will be large, and so the coefficients cannot be estimated with accuracy. So it's a problem of accuracy, it's a problem of prediction if the moderate multicollinearity problem exists. So two important detections we have. In first case, the standard errors are infinite. In the second case, the standard errors are large. But most importantly, if the multicollinearity problem is moderate, then the regression estimates can be computed but not with absolute accuracy. So that basically boils down to the problem that why is it important in the context of a regression model. Now we proceed for the consequences of this problem. So we have observed in the previous discussion that multicollinearity is a problem of association among the independent variables, which is highly pronounced in case of a multiple regression model, where more than one variable affects a dependent variable. Secondly, multicollinearity can be high, can be low, can be moderate. If it is very high, then the standard error will be infinite and we cannot estimate the unknown parameters of the population. If it is low or moderate, then estimates can be done, standard errors will be very large, but it cannot be done with perfect accuracy. So now we are going to proceed on what are the consequences of this problem, because what way the estimates are affected if there is a presence of the problem of multicollinearity. So to come for the consequences, the first one we look for the best linear unbiased estimate property, which we say the blue property. So in the presence of the multicollinearity, the blue property will be restored, but the OLS estimates will have large variance and covariance, and because the variance will be very large, precise estimation will be difficult. That means if the variance is very high, that means the dispersion or the variability of each observation from its mean will be on the rise. So as a result of that, large variances will affect the problem, and this will keep on consistently affecting the statistical significance of the unknown parameters. So the very first problem is very clear that the OLS estimators have the large variance, and that is one of the detection of the problem that this is present in the data set. Secondly, we talk about the consequence 1, where because of the large variance, the confidence intervals tends to be much wider. So if the confidence interval tends to be much wider, then as a result of that, the null hypothesis rejection will be actually very less. So this type of problem will result to insignificance of the explanatory variables. Because if the standard error is very high, then automatically the value of the test statistic will be small, because we know by test statistics standard error lies in the denominator. So if the denominator is on the rise, then the value of the ratio will fall. That is, any kind of test statistic, whether it is t-test or any other test, that will keep on falling. And as a result of that, it will not be able to exceed the table value. So the consequences is very clear that the estimated coefficient will be insignificant. So there will be a greater possibility of the acceptance of null hypothesis, and which is also reflected in the wider confidence interval. Because in the confidence interval theory, if the value of the test statistic lies within the range, then the null hypothesis gets accepted and the estimate becomes insignificant. So the first consequence is about the standard error or the standard variance, which is very, very high in this case, which will make the estimate to be not to be precise or difficult. Second one is regarding the possibility of the acceptance of null hypothesis, or less possibility of the acceptance of alternative hypothesis, which means that the confidence interval will become more and more wider, and thereby the estimated coefficient will not be significant. Keeping track of these two problems, the third consequence is about the t ratio. The t ratios, which means the value of the t statistic of more than one variables, will be statistically insignificant. This is an indication that multicollinearity is present in the data set. So in order to detect the problem, we have to check whether in a 4-variable regression model, where there is 4 independent variables affecting the dependent variables, almost 3 of them are insignificant. This is an indication that multicollinearity may be present in the data, because the t values are insignificant one after the other. So which means that the variables are correlated with each other. So this is one of the detection of this problem, and automatically this is one of the consequence of this problem. Fourthly, we observe another very, very important observation, very crucial observation, that R square is very high. We know that capital R square stands for the overall significance of the model. That means how all the variables or the slope coefficients jointly explain the variation in the dependent variable, and thereby overall what will be the nature of the R square or goodness of fit. So if the R square comes out to be very high, which means almost the explained variation is near to 100%, and which gives us a kind of a confusion or ambiguity or some kind of contradictions, that this model has a problem of multicollinearity. So these are the symptoms. So R square maximum value can be 1 or 100%. If R square becomes 98% or 97%, it's an indication that somewhere there is wrong in the data, or the variables are associated with each other. So two very, very important indications of the problem or the detection of the problem. The first problem is regarding the t values which are insignificant, and secondly R squared is very high. So these two are indicating that somewhere or the other multicollinearity problem is very much present in the data set. So OLS estimators and the standard errors can be sensitive to small changes in the data. So if after detecting the problem any kind of correction is being done, then we can take care of these two problems. So that means among all the 5 consequences, the 3 consequences are very pertinent. Firstly, we talk about very high standard error. Secondly, because of high standard error, the range of confidence interval becomes wider, which makes acceptance of the null hypothesis to be more and more pronounced. Thirdly, the t ratio will be very, very less, which means the computed value will be much less than the table value, which will accept the null hypothesis, which means that the estimated figure is insignificant. And finally, the goodness of it is very high. That means all the variables are together affecting the dependent variable, and the explained variation is close to 100%. So if these two events occur simultaneously, one, very, very low t value and very high R square, then we can confirm that multicollinearity is present in the data set. So this calls for some of the rules of thumb for detecting the problem of multicollinearity. So the first rule of thumb is actually being detecting the problem, which means high R square but very few significant T ratios. So in a multiple regression model, we generally work with 5 to 6 independent variables. And among 5 to 6 independent variables, we observe that only 1 or 2 variable is significant and others are all insignificant, but capital R square is very high. So this gives us a problem to recheck about the estimation process, to recheck about the data or about the variables, because this is a clear indication of multicollinearity problem. That means individual t-test or the partial slope coefficients are actually not statistically significant from 0, and which makes t ratio to be very low but capital R square to be very high. Secondly, we observe about the pairwise correlation. Because before running the regression procedure as per the steps, we need to go for the scatter plot and we need to check for the correlations. So if we observe that there is a high pairwise correlation between the regressors, then definitely we will be not taking all the variables together in the regression method. We will drop or we will consider one at a time. Because from the correlation matrix, if the value of the correlation coefficient appears to be more than 50% or near to 1, like 86% or 89% or 90%, then it's a clear indication that those two variables cannot be taken together in the regression estimation exercise. So this is actually the importance of pairwise correlation, which also detects the problem of multicollinearity. Then we have the problem in case of the simple correlation or the partial correlation. So if we look at the partial correlation, then also it's an indication that multicollinearity may be a problem. So this goes for examination of partial correlations. So partial correlations means that the regression of y on x2 when x3 and x4 are remaining constant. So under this condition, again we find out capital R squared is very high because y is regressed on x2, x3 and x4 are given. If capital R square is very high, but the individual partial correlation coefficient, that is the small r square, when it is done between x1 and x2, x3, x4 are kept constant, or done between x1, x4 on x2 and x3. So when these are done in pairwise manner, but the partial correlation coefficients, and if they appear to be very low, then also it's an indication that the variables are highly correlated. So in case of partial correlation coefficient, the symptom is they are very low, but capital R squared is very high. So two important symptoms. The first symptom is very low t value, but high capital R square. Second symptom is there is very, very high correlation coefficients. But if we look at the partial correlation coefficients among the variables, they are low, but capital R square is high, which can actually detect the problem of multicollinearity. So in order to go for the problem of multicollinearity, we need to devise about the corrective measures. What can be the corrective measures to get rid of this problem? Now we proceed for some of the factors or some of the steps to diagnose this problem. Because first of all, we have to identify the problem, detecting the problem. We have already done on the consequences of this problem. And now we proceed to the diagnosis of this problem. That means how the problem of multicollinearity can be corrected or what can be the remedial measures. So to go for this, first of all, we go for the issue of tolerance. Tolerance refers to acceptability. It means that a measure of the percentage of variation in the predicted variable that cannot be explained by the other predictors. For example, a very small tolerance means predictor is redundant. So in this case, we all actually want to say that if the tolerance level is very low, then multicollinearity problem is present. That means how can we tolerate the association among the variables? If it does not affect the estimates too much, then we can go away with it. Otherwise, if the tolerance level is more than the acceptability limit, then the multicollinearity problem needs to be corrected or detected. So this goes for, to understand the tolerance level, we actually have to compute a statistic which is called variance inflation factor or VIF. So this variance inflation factor is the indicator that the other independent variables have on the standard error of the regression coefficient. That means the other independent variables, meaning the variables which are not related with each other, what is their impact on the regression coefficient, and we go by the VIF or the variance inflation factor. So variance inflation factor is inversely proportional to the tolerance. That means if the variance inflation factor is very high, then the tolerance will be less, and accordingly we have to get away with the problem. If the variance inflation factor is very low, then the tolerance is higher. So tolerance and VIF or variance inflation factor are inversely proportional to each other. So there is a rule of thumb that if the VIF is very high, then there is a high degree of multicollinearity problem, and which is actually more than 10. So the rule of thumb is that if VIF is more than 10, then the problem of multicollinearity problem is there and we need to check it. But if it is less than 10, then the tolerance level is very, very high, and so we can continue with this problem. Otherwise, if it is more than 10, we need to drop it. So this particular table or this particular result actually identifies whether the problem is there or not. So we observe that for the x1, x2 and x3 are the three independent variables. For x1 and x3, we find out that the VIF is 2.72 and 2.51 respectively, and they are less than 10. But for variable x2, it is 14.865. So this basically points out it's more than 10, so we cannot continue x3 in the data. We either have to run x3 separately or x3 has to be dropped from the data set because it is indicating the problem of multicollinearity. Now we observe the remedial measures. So what to be done finally? So what can be done if the multicollinearity problem is serious? That is how we project the problem. Because if the problem happens to be a serious problem, what can be done? First solution is no action, because we cannot actually eliminate the total data set. So you have no choice over the data. Either you have to go for a bivariate regression one at a time. So we cannot continue with the multiple regression model given the peculiarity. So this is one of the basic problem that we have to carry out with the multicollinearity problem, and there is no way out. And secondly, we need to follow some rules of thumb. And that is one of the corrective measures which we can go for. So the first corrective measure is that increasing the sample size. So if the sample size is increased, then it might happen that the variance inflation factor will become less. This is because covariants are inversely related to the sample size. Because if we refer to the covariance expression, then sample size comes in the denominator. So with the rise in the number of observations, the covariance will fall. So association among the variables will be less. So the solution works only when multicollinearity is due to the measurement error. Measurement error means there are lots of omitted variables which were not taken up. Now as I increase the sample size, as I increase the number of independent variables, those are incorporated. Or it exists only in the sample and not in the population. Because if it is in the population, it's a perennial problem. If it's in the sample, then increasing the sample size can remove the problem of multicollinearity. Secondly, which is done by most of the times or majority of the times, this technique is followed by dropping one of the collinear variables. That means we are going to drop the variable which is basically creating the problem, and we are basically running the regression one at a time by dropping the variable. This is one of the most important steps that is followed to detect and to correct the problem of multicollinearity. Substitution of lagged variables are also being done. So if we have a distributive lag model where the lag dependent variable can be used, then if we substitute by the lag dependent variable, then this problem can be eradicated or can be eliminated. We can also add on some of the external variables to or control variables for this problem so that they are treated as instruments and they can capture the problem of multicollinearity. Or we can also add some additional equations in the model. This is done in a simultaneous equation modeling. Some additional models can be taken up. Or there can be a method of principal component analysis where the variables are converted to different components. Each component is an aggregation of the variables and the components are not correlated with each other. So this is one of the most common exercise that is being done if there is a problem of multicollinearity. So when we come to the sum up of this particular module, we observe that first of all this module deals with the definition and the concept of multicollinearity, which means association among the variables, which basically ranges from no collinearity to very high collinearity. Next, we talk about the consequences. The consequences are very clear. Firstly, T ratios are very less. Secondly, capital R squared is very high. Thirdly, the partial correlation coefficients are very low. And fourthly, majority of the independent variables are statistically insignificant. This is an indication. And then we have the solutions. So in the solutions, one way is to drop the variable. The other way is to go for the principal component analysis. The other way is to increase the sample size so that the problems can be eradicated. And in that way, the OLS estimates will be found to be consistent and there will be accuracy, or it can be done with a precise of the total estimates after the OLS.